It's having trouble. Okay, all right, excitement, yes. So 5 weeks until Thanksgiving, when you forget everything. The fall semester is a funny structure, right? You have this long march, and then Thanksgiving, and then one more lecture or something like that. Yeah. And if you had exams, it'd be like, oh my God, no idea what I'm doing. Strange structure. All right, so let's see. So things are working. I've put up a few more. So there are slides coming out. There'll be a tweeted set of slides every day. So contagion. I'm going to talk about contagion. So important business, obviously, and then social contagion. That's coming after that. Eventually we'll get to scaling. That's a huge thing, but we'll also find out how to become famous, which is cool. Yeah, and then other little things in there. Look at this. They love this word, right? When a stock market theory is contagious, lots. It's used all the time. Okay, yeah, right. So here are our new sets of slides. Good stuff. Homer Simpson is involved for some reason. Superstardom, and then contagious stories, and then scaling. So this is a big story about scaling. So that's a huge, huge thing. It covers, every biology, Moore's law in computer science, industry. There's an unbelievable amount of things. Okay, all right. So first we're going to get through the rest of networks, and the first thing is to talk about. Okay, so I'm going to talk about scale-free networks. So we had a lot of fun with. Maybe you didn't, but I talked a lot about small world. Let me be clear. I talked a lot about small world networks. The next piece is, in these huge blockbuster kind of papers early on, or ideas early on that set the whole thing off, is the scale-free networks business. All right, so a bit of a funny, you know about this power law scaling thing, right? You've worked at those. The next assignment includes some more questions about just good old power law size distributions. We're going to have a few more of those. One thing we'll get to is the 99% story, right? 80-20 rule is related in there as well, right? The idea that 80% of the population has 20% of whatever it is, money, and the reverse might be true. So we'll have a look at that as well, because that's a little more complicated. Okay, scale-free networks. So it's a bit of a funny term, but it's really this, right? So that the degree distribution has this power law tail, right? So the number of friends. So if you and so to be specific, because this matters tremendously. But when you start to think about these things, if you randomly pick a node, that's what we're doing. We're randomly picking a node and looking at how many friends it has. We'll see that it's quite different if you randomly pick an edge. That's a different business, and that's quite important for spreading and contagion. It's fundamentally important. Okay, so we've talked about this one. I gave you a bit of stuff early on, but so it's the emergence of scale. So there's a good title, emergence of scaling in random networks. So it's a special kind of randomness. So I'm going to say, this scale-free. It's what everyone says, but it is a little bit odd because when you think of scale-free, when you think of network, it's a physical thing. So you think of the network being scale-free. But it's really about the degree distribution, which is a somewhat lifted aspect of it. So it's not fractal, right? You might think about it being fractal. And we'll talk about when we go to scale. This end part where I talk about allometric scaling, we'll touch on that. That's a part of it. So we're talking about links that are actually quite abstract usually, right? They're somehow or informational. They're not necessarily, but certainly this is true for physical ones. The problem is, for physical ones, the ability to have giant hubs becomes limited, right? Because if they're really physical links where you're really moving stuff around on those links, then that becomes hard to manage. You might say, all right, well, something like Google it is physical because it's on the web and there are computers everywhere, and that's true, right? And so what's happening there is that you don't have a little node on a page. Google is not one little node on a page, and my website is not one other little node on a page. You can draw them like that, but it's very deceptive, right? Because Google is this massive distributed set of computers. All right. Okay, that's very nice. I feel relaxed. Okay, so right, the hyperlink network of the web. It's a lot. There's a lot of arguing actually about the internet. That's a bit different. And you'd think the internet, oh, we should just have a map of that, but that's a bit messy actually. That's a bit hard to figure out. Strangely, so is the power grid. I mean, you just think we'd have a map of that, but that's well, private. So there's a lot of arguing about whether networks are scale-free. Okay. But generally speaking, these things appear a lot. So this is from the original paper. So you can look at these and see what you think of these for power law size distributions. We will talk about quality of scaling again a bit later on. So 3 orders of magnitude here. And what do we have here? 6, 10 to the minus 6, no, 10 to the minus 1. So 5 orders of magnitude here. So that's the sort of thing you want to think about the range. And what do we have? So we have, this is a World Wide Web. This is the web for the Notre Dame the website. And this is in 1998, 9, right, when they measured this. It's sort of the little ecology of pages for that particular corner of the web. You know, which pages pointed to each other. This one is for the actor graph, if I got that right. Yeah, and then and power grid, which is a funny business, right? No, this is active collaboration. Sorry, I'm reading it wrong. This is active collaboration. This is the World Wide Web, and this is the power grid. So this one is kind of funny. This is a 10 to the. This is a minus 4. This is a very steep exponent, and so you know, right? So now we understand. This is gamma is 4. Right between 2 and 3 is when you have a finite mean, infinite variance. That's a sort of statistics of surprise situation. This is very much not in that category. And in fact, this has sort of later been understood to not really be a power law, right? So this was okay, but it's very different scalings. That's an important thing here too. They're very different scalings. This is sort of 10 to the minus, this is not 10, minus 4 scaling. I keep saying the wrong thing. 1 order of magnitude here though. So that's a little dodgy. That's dodgy, okay? So if someone says, I have a power law for you, you have to say, and you know, they want some money for it, then you have to ask them, show me a picture of this power law, right? And if they show you a power law with only 1 order of magnitude at the bottom, then maybe you shouldn't give up your money for that one. All right, so the exponents are 2.3 measured here, the dashed line for the active graph, which again, a very funny graph, right? If you're in the same movie as someone else, you're connected to them. And you can see there's a lot of strangeness here. And the World Wide Web, this is 2.1. It does look like a pretty good scaling. This 3.5, that's 4 orders of magnitude along the bottom. It's not bad. And then 4 for the power grid. So that's a bit sketch, that one. But these two are in this statistics of surprise situation, right? High mean, actually the mean is starting to get big, but the variance is large. All right, so we're looking at real data, which is always a dangerous thing to do. So an anecdote in here is that Barabasi, at some point I was talking years ago, and he said, I think a colleague of his, who was a pure mathematician, figured a lot of this out, thought about, well, what if we have these random networks and they have these heavy tail distributions for degree? Let's do it, right? And all these interesting properties came out, but they were pathological. Like, why would these things appear? So he just sort of put it off to the side. Had some fun with math, you know, because obviously it's the Poisson degree distribution things. That's what random networks are. So as I've said, it turns out to be the opposite. You never find Poisson degree distributions in the real world. You find them in your head. You do not find, and you do find these. But if you're a pure mathematician, you might discard them. All right, so a couple of examples. So these are just random networks with the largest components. And so they've been randomly put together. They have an exponent 2.5, so it's a power law size distribution, right? For degree, so we do this thing where we make the distribution, we select a bunch of degrees, build the nodes, so you give them, you know, if you have this one has 1 friend, so it's going to have 1 friend, and then start to connect them up. And I gave you a little quick explanation of how that works at the start of this models and networks business. And so you can see hubs appearing. All of these are just random instances, right? So you make a bunch of, you create a bunch of nodes by sampling from a distribution, then wire them up once, 1 wiring. And so you can see this one, we sampled from further out in the distribution. You've got a bunch of hubs in here. And because of this power law, and so these are thinner though, you don't really notice that that's maybe of that same group. These are all from the same family. They're samples from the same family. And so power law size distributions are weird things, right? Most of the time nothing happens, and especially for this kind of exponent, 2.5. Most of your samples are somewhat small, so there are lots of little characters out here with one friend. Now and then you get a big one, right? Now and then you get a big one. And if the size of your networks isn't too big, well, there's going to be a lot of fluctuation with what's the biggest. Okay. All right. So that's just making a few. We're going to go and see if we can create we're going to follow what they did to see if we can understand a mechanism for this. And then we'll go on to Krapivsky and Redner's approach. So Sid Redner, who's now at the Santa Fe Institute, was at BU for a long time, came up with an alternative approach to this, and we'll see it all connects back to Simon's model, which at the time was not seen, right? It was not seen. Okay, so I prefaced this a long time ago when we talked about Simon's model and Mandelbrot and their argument. So yeah, there was cumulative advantage was one of the original terms to solve the price, and then what we'll have here is preferential attachment, but you're going to see it's some sort of variation of it. All right, so does this exponent gamma, how much does that depend on the mechanism? So we saw how that depended very clearly with Simon's model, right? So Simon's model, you had the rate at which a new character appeared, right? So it could be a new city is started by an individual moving to a new place, or it's a word you haven't seen before in a book, right? This sort of thing. So the novelty factor, what's the rate at which novelty arises, was connected to the exponent, and you could dial that, right? So you dial the rate at which things came in, you got the exponent to go from 2 to infinity, I think, right? Very steep. Do the details matter? So this is something to explore, and you have an assignment question where you can play around with this. So there are natural things to try and change. All right, so let's do the model. Yep. And it's known as the BA model. You'll see this. Preferential attachment is their big story, and of course, growth, right? So this is good. We're actually trying to build this thing. I'm going to march through the whole thing. So we're going to start with disconnected nodes. So we have some number, right? Some number. You just start with a few. It doesn't really matter. It doesn't have to be thousands. Just a small number. We'll do this thing where we add a new node discretely at every time step. So that should be reminiscent of the Simon's model, where of course there wasn't a network. We weren't thinking about a network, but it's reminiscent of that. And each new node gets to add a bunch of links, right? So they're going to add links to the nodes that are already there. And we'll use, this should feel like the Simon, which I know is in the distant past, but preferential attachment. So that probably you attach to a node of degree k will be proportional to that degree. Right, so you preferentially want to go to nodes of higher degrees. So this worked before when we had Simon's model. If we have 30 people living in this city and 10 people living in this city and 3 people living in this city, then the chance of getting to this one is 30 divided by 30 plus 10 plus 3, which I believe is an excellent. So this translated to 30 over 43. This one is 10 over 43. There are just these 3 worlds, 3 over 43. And the way this was done is because you randomly chose an individual in here, right? So you randomly choose an individual and then you go and live in their city. You don't think the city is of size 30, so that gives me this chance. You actually just randomly select from all the individuals. So that was a simple mechanism. So the version that we're looking at now is you have, you can't quite directly do this, but you have a node that has so many friends already. So let's do another example. What have I done? 4, 8. This one has 8 friends. This one has 4 friends. And there's going to be a whole bunch. You have to think about how many friends these guys have, right, as well. But the chance of connecting to this node is 8 divided by the sum of the existing degrees. And this one is 4 divided by the sum of existing degrees. Does that make sense? So instead of it's not the population now, you're going to a node and you're going to connect to it based on its existing degree. So it's a rich gets richer thing, and it's Simon's model, sort of, right? We've seen a lot of this before. So it popped up again because it popped up again. That's part of why this is in the course a couple of times, and you'll see a different flavor here. It's because it's just such an important thing in reality. The universe does this over and over. All right. Okay, so let's. This is not quite. There's some variation on what was done in the paper, but that's okay. So I've changed things a little bit. So we're going to use this term. This actually comes from Krapivsky and Redner. It's the attachment kernel. We'll have this term. A sub k is the attachment kernel. So it's not a probability. From this you get a probability, right? So the attachment kernel for these guys is just their number of friends. So 8 here and 4 here. But we could start to vary this, right? We could say number of friends squared or anything you want, exponential of number of friends. You could play around with that. So the attachment kernel is a weight, right? It's just a weight. So each node gets a weight, and to get the probability, you sum up all the weights, and that's your normalization factor. Okay? So the attachment probability, we'll write it like this with a nice big fat attach there. So this is at time t. And so the probability you attach to node I, this is exactly the model they used. This is exactly the way to put in so-called preferential attachment. That you attach to node I, well, it's the degree of node I divided by the sum of all of their degrees. So more generally, this is an attachment kernel, A sub k, divided by the sum of all the attachment kernels. So you think of those as weights. Okay, so the number of nodes at time t, so this sum goes from j equals 1 to the number of nodes at time t. That's the number of initial nodes plus t. So at time 0, there are some initial nodes. We put a little soup of nodes. We connect them up a little bit. And then we add one at a time. Right. Yeah. Okay. So we can translate this over and make it a little bit simpler for ourselves, look a little bit better. And we start to get at the thing we're after, which is the distribution of nodes of degree k. I know this is thrilling. So we're going to change the sum. Instead of summing over all of the nodes that exist, we're going to each one, we're going to say, well, let's class them. So let's count up the number of nodes that have k friends. And if you have k friends, you contribute k. Each one of those has degree k. And then we're just simply going to sum from the minimum degree to the maximum degree, which in principle is 1 really, but yeah. Okay, yeah. So, right, so n sub k, it's the degree, number of degree k nodes at time t, right? That's the same sort of thing where we're finding the number of cities of size k or the number of words that appear k times. Yes? Yes. Okay. It's pretty good, so we're going to do a similar kind of business, but we'll somehow, instead of a difference equation, which is what you work through for the whole, and you enjoyed all those gamma functions and things, bonus beta function, just amazing, right? You can take a different path. There's still probably less monks maybe, but where you end up with a differential equation. All right, so the n plus 1th node, we're going to stick that guy in. And what's the expected, so you see this kind of business again, what's the expected change in the degree of the ith node when it gets one more, right? So this is at time n plus 1, and this is time n. What's the change? So it's the way this model works is it can only be plus 1 or 0, right? Either the new node comes in and attaches to it, or it doesn't. So it's going to be plus 1. That's really what this is. I know what I could do with that. I know, yep, sorry, plus 0. So think of it like this. There's a plus 1 times the probability that that node gets attached to, plus 0 times the probability that it doesn't get attached to, and the 0 cancels it out. So we're getting the weights of these two things. So the probability that you get attached to, well, there's the degree of the node. This is our probability of attachment, the degree of node I, and you have m chances to do it. So this number is going to be pretty small. This probability is pretty small. So this is an estimate of the actual probability. Right? So this is going to be very small. This is as the thing grows, 0.000. So the usual business is we say, okay, this is going to be incremental. We're going to think about over a long period of time. Its degree is sort of going to grow fractionally, which is kind of crazy. But we'll transfer it into this sort of continuous business. A nice thing about this treatment is we're actually going to track node i's behavior. And so we'll see how the degrees grow. So you'll see the whole evolution of individual nodes' degrees, which is kind of how this gets richer model is working locally, which we didn't really see before. We didn't quite see it before. Because we went to the groups. We went to groups. We moved away from individuals, went to groups. All right. Okay, we're going to get rid of the expectation, that same kind of business, that over long time periods, there'll be kind of this smooth growth of degree, which is okay. It's not bad. And then we'll do this next business where we'll say, okay, let's replace this guy, usual sneakiness, or more unusual sneakiness. I don't know if you want to say it. So let's see, we've got ki at time n plus 1 minus ki at time n. And on the bottom, you can say, well, right, so this is time n plus 1 minus time n. So this is delta, this is the change in n plus 1 divided by the change in time, which is just 1. Change in time is 1. So then we're going to approximate this with dki n plus 1. Because we're physicists and we just don't care. Meanwhile, there's a mathematician on the ground, they're trying to wake him up. It's okay. I'll give you some things to write about. Okay, all right. So, fear and loathing. Okay, so we replace it with a derivative, and then we're like, oh, we can solve this now. It's a derivative, right? So the differential equations classes that you take, yeah? So you spend all this time with, separable equations, they're good. So you do a lot of those. Integrating factor is good too. Yeah, that's good, so let's do that a lot. And then at the end, if you're really lucky, you get up to linearized things, which is fantastic, right? Matrices, eigenvalues, stuff, really good. So it should all be that, basically. The first part is just because we can do those, we can do those. So now we're going to give you 100 of them. Doesn't matter if nature produces them or not, right? Anyway, all right. But this is a nice moment where, in fact, one of those guys applies. All right, let's see. So we're going to deal with the denominator. So, okay, let's on the right-hand side, we have a bit of a messy thing. But we'll see this is the same as summing up the groups, what we did before. So we're summing up the, okay, I've written it back this other way. We're summing up the degrees that exist right now. And we know we had some initial number of edges, which we don't really care about. And then every time someone comes in, we add m edges. So that's m edges emanating from that person and m edges emanating from the nodes out here, right? So your average degree is going up by a factor of, or the contribution, so the total degree is increasing by, if you add up all the degrees, is increasing by 2m. Right? M from this one, m from the others. Okay. That's what this little, not a lie, says. It depends if there are initial edges and so on. It's a little bit of a fudge at the start. Because you want to connect some of them at the start. You do. Okay. Because if you have 0 friends in this model, you will never get a new friend. It's very sad. You just will never get a new friend. Because the probability of you connecting is 0 divided by the total number of friends so it's very sad, really bad. So you can mess around with that a little bit. Everyone gets a +1. And in fact, that's what the solar price did in the 70s or 60s. Okay, so it's going to be 2tm, right? So after t time steps, every time you've added m new edges to the thing, and each edge has 2 ends, so we've got 2m times t. I don't know why it's 2. Should be 2. Poor form. This should be 2mt. Okay, good. So that's our denominator. So now we've got this derivative. It's going to simplify spectacularly. And in this way. So we have a 2mt on the bottom, and I've got it the right way around. These guys cancel, and on the bottom we just end up, so it's 1/2t times ki. That's good. So that m didn't really matter, which is useful. You don't want, it's nice when the details don't matter too much, right? Physicists kind of hope that. All right. Okay, cool. So we can rearrange this. Look at this, it's great. Look at this thing, it's great. It's the ith node's degree. And the ith node comes, we have to think about when that comes into existence as well, right? So we have m0 nodes to start with, and then they start to come into, they're born at some point. Yeah. And we have this. All right, so let me write it like this. I know I've got it there on the board, but this is fine. So what is this thing? What kind of differential equation is this? Apart from an awesome one. What is it? Separable. Separable, right. So you can put the t's on this side and or on this side and the k's on that side. So that's pretty good. They actually exist. All right, so you can do this. We can put the k sub I over here, so it's dki over ki, dt over 2t. Yeah. You want to do that? You guys can do that. Let's do it. All right, it's great. So let's put this over here. I hate it when people do this. You erase the thing you had. That's terrible. Okay, so I did it. I'm so bad. Okay, so we've got dt over 2t. So let's integrate these things. Left-hand side is, yes. This guy? That's a 2t, yeah. Mm-hmm. Good? Anything else? Mm-hmm. So let's make it plus ln of c, because that's cool. All right? Which is, right? Log goes from minus infinity to infinity. This is totally cool. This is a good thing, right? Yeah. So c goes between 0 and infinity. Even better. So this is log c t to the half. This guy goes up here, and then they join up because they're pals. So we have, it's growing like this. It's growing, there's a square root. So this is a newer kind of, we didn't see this before. So depends on when they come into existence, and we'll have a nice way of figuring this out. When they come into existence, that matters. So if you're early on in the game in this thing, because it's not quite, I mean, it is stochastic if you simulate it, but we've turned it into a very deterministic thing, then you will just get more and more friends, right, at a faster rate. So it's a first mover advantage situation. Here it is, good. But we have to figure out, this c sub I is going to matter. So it's going to actually be node dependent, right? The constant's node dependent. Yeah? Cool. Okay, so the ith node appears, so it's a little bit funny, but there's some initial number of nodes. The start time for the ith node will be I minus m sub 0, because there are m sub 0 nodes to start with, right? So if there are 4 nodes to start with and you're the 1004th node, you come in at the 1000th time step. And the first 4 appear at 0. Okay, so that's a little bit of a fudge, but not worrying about those initial nodes, we can get this reasonable result. So let's see. Oh, yeah. Let me do this for you. So we're going to have to figure out what that constant is. And it turns out you get this. Okay, so that the degree of the ith node will depend, that's its start time here, will depend on its start time. And so it's normalizing this. But it grows like that to a power of a half. But it only exists after t, after it comes into being, of course. All right, let me being bad with words. Okay. So it's, you know that when it's, okay, so when t equals ti start, right? So when t equals ti start, node I appears. And by the construction of this thing, it has m friends, because each node that appears makes m friends. With m friends. So you can, right, you've got a constant, so we have this, right? So we have t equals ti start, so this says ki at time t I start. Is that the way I'm writing that? Yeah, right. Start equals m. So this is this is a condition, right? And we had this formula, ki of t is equal to some constant times t to the half. So the sneaky thing to do, the very sneaky thing to do, is to say, well, let's call this some other constant, and let's make this t over ti start. This is okay. We're just going to sort of essentially break this constant into two parts. We'll say it's still some constant out here, and we'll put ti start in here under the brackets. And the reason for that is when this is 1, this is now 1, when t is ti start, and we can easily see that this must be m. So that's a bit sneaky. The other thing you can do, of course, is just put in ti start here, put m here, and you'll get a constant for this guy, and then you rearrange it and you'll still get the same result. So it's okay, but it's just standard differential equation thing. Okay, so all nodes are growing as t to the half, but the later nodes are damped, right? Because this is a constant for all nodes. This is growing as you go through your list of nodes, right? So if you're the billionth node in this thing, bit of a Ponzi scheme situation going on here, or Amway built in. So who else can we defame? What else is there? You shouldn't do that. No. Ponzi scheme. That's good, right? You go to jail for that. Yeah. Okay. Okay. So as this gets bigger, then the whole you can imagine, right? This is just dampening this thing. Right? It's being squished. First mover advantage. The early nodes are doing best. Yes. It's a Ponzi scheme. Yes. All right. So here's a pretty awful plot that I made a long time ago. My design aesthetic has improved. All right, so here's KIT. This is for a bunch of initial conditions, starting at 1, 2, 5, and 10, just using that formula with adding 3 nodes. And so here they are, 1, 2, 5, and 10. They're all growing as the power of a half. T is the power of a half. But they start at different points, but they're being very damped, right? So this is how this whole thing kind of plays out. Right, so if you start right out here, the chance of getting new friends is really kind of bad. No matter what they tell you, you shouldn't join the network. Don't look at their things. Okay, so what you have to do at some point t in the future, so we're going to go right out here, we'll have all of this ecology of nodes, right, that have grown. You can have some with lots of friends, and then lots of them are just struggling along the bottom. And then we want to take that and say, what's this distribution of friends that they have? Right, so early on, there's just a few. We want to turn this thing into a probability distribution. We want to take a snapshot and say, boop. And somehow that's got to be a power law. So it's not completely obvious. I mean, t to the half is sort of weak. It's not like these guys aren't running away with the game, sort of thing. Right, they're not going super. So we have to do a little bit of sneakiness to sort this out. All right. And there's a really nice trick here. There's always good tricks. Okay. But you kind of get this idea, right? So we figured out how these things grow, right? The ith node, it appears at some time, and its degree will slowly grow. It'll grow as a power of t to the half. Of course, only starting when it comes into existence. And it will be dampened by this factor of which is its start time. Right? There's a 1 over start time to the half on the bottom. So we're going to get more of these guys in a sense and less of these guys, and that's our power law type distribution. Right? Lots of little ones, then some more at the next level, and then a few, that are just killing it. All right. Okay, degree distribution at time t. So we're going to use a sneaky fact, a good thing, which is the probability that of start time. So again, we've done change of variables a couple of times, nothing too, evil. And we're going to do, we'll use this fact. So we know the distribution of start times really well. It's a uniform distribution. It's growing and stretching out. So at some time t, the distribution of, this is the probability, if you randomly choose a node, right? Now so forget which order they came in. You're randomly choosing a node. This is 1 over t. This is the probability that a random node has, a random node starts at time t, or started at time t. Let's call this t. Let's do that. All right. It's a uniform distribution, right? Because they're just coming in one at a time. There's nothing special about that. All right. So we have this. The probability of start time is 1 over t dt. This is 1 over t is the probability distribution. It's just flat. It's a horizontal thing. We have a connection from degree to its start time. Right? T is this overall factor. It's just how long the thing has been growing for. We kind of hope that will disappear. That worked again for Simon's model. Well, we assumed it was true. That after a long enough time, the distribution would saturate and have a particular form. So we have a connection between the degree of node I and its start time. So if we rearrange this, all right, let's rearrange this. We'll square this side, square this side. So we have a k squared and m squared. And this is gone. So the k squared and m squared are here. And we want to bring the start time up here. So we go, that's an important noise. You go, and then there's t to the half gets squared, so you get a t there. Okay? So you understand? All right, good. So the start time is, this is a bit of a funny thing to think about, but at time t, the start time of the ith node is decaying like its degree to the k, 1 over k squared. So, simple distribution, right? Mild distribution. There's nothing, well, I mean, it's uniform. It's a bit funny, but there's nothing super crazy about this guy. Has an average, right, in the middle. It's a bit funny, perhaps. And here's a start time connected to this. It's an inverse power law. So this is exactly this case where we have a nice distribution that's well explained. We have an inverse power relation between two parameters of the situation, and then the other one ends up with a crazy power law size distribution. So we're going to transform variables. We've got this guy. Let's differentiate this with respect to degree. So dt dk. Do this guy, right? So it's a 1 over k squared becomes, right, minus 2 over k cubed. Good, healthy, nothing bad. There's an m squared on t on top. That's just sitting there. So this is really where the whole thing is coming from. There's this 1 over k cubed. That's the power law. That's going to be the power law. Okay, so we're going to stick things together. We have the probability of degree k, dk has to be connected to its start time, d start time, and then we start to put everything together. So, yeah, we want this is the Jacobian, so these guys cancel to go back to here, dki, okay, we need this guy. So we're starting to fashion it. This is the thing we just calculated, absolute value of it. There's a 2m squared over t, there's a k cubed on the bottom. I know I'm just saying words. And then there's a 1 over t for that uniform distribution. So some nice things happen. These guys cancel. The t's go away. We're going to rearrange things a little bit. And there it is, right? Sort of a rude thing to have done. But the t's go away, so that's good. So there is a saturation story here. And you end up with k to the minus 3. So the probability long-term for this model that you have a degree k, decays is k to the minus 3. So there's no tuning in here, right? The m's have disappeared. Well, there's an m sitting here, but it doesn't affect the power, the exponent. So this is a science paper, right? Science paper, it's 1998. The thing was, essentially, here's a mechanism that produces one specific power law with its exponent -3, the 3 examples they showed were 2.1, 2.3, I think, and 4. So they're a long way away from that. But this is just where things were. It was enough to show that you could get a power law size distribution from a model that was plausible for growing random networks. Almonds. Okay, and but the matchup is not there, which is what you want in all the time, right? The people will quibble, and we'll have a nice quibbling about this when we talk about scaling over a 12th, right? Exponents that two theoretical exponents that differ by a 12th, and you have a holy war about it. These are differing by 1, which is huge for gamma. There's a big difference. If gamma is between 2 and 3 versus 3 and 4, you've gone from the statistics of surprise into the Snormels situation. It's not very exciting. Okay, so we have a very specific prediction. Obviously, I've said this, so real networks are between 2 and 3. Yep, and we know this story, so 2 and 3 is the finite mean, infinite variance. Yep, and this is then a bit of a snoring one, so we have wild versus mild. Okay, so it's not quite getting that, but it's getting at it. These are again, right, these are the things. This is let me get it right. This is actors, this is it's down the bottom. 2.3, 2.1, and 4. So it's not a match, and they're not, this is the line of fit, it's not the theoretical line. The theoretical line is absent from these plots. It's okay. A couple of others, you can play around with all sorts of things. So it could be that the in degree and the out degree are different if you've got a directed network, and so these are older observations. Words, again, that's a thesaurus thing. The internet, as I said, is a very different story altogether. But this has been measured 1 million times. Lots of situations. Okay, all right, that's the story. But obviously it's failing, so we have to figure out how to tweak it. We know there was something with the Simon model, of course, right? That did seem to do the job, but all right. So you can vary the attachment kernel. So instead of just being explicitly the degree, you can add all sorts of other things. So edges could fail or move around. So they could be deleted, they could be rewired. Okay, exciting. All right, you may deploy food. I brought bananas. Is that just wrong? Who wants a banana? These things probably have to bypass you, and then you can. Wasabi almonds. All right. Sorry. Look at these guys back here. Yes! One for you too. That's chocolate, all right? So they're hard to open, which is disappointing and frustrating. But I'm sure you can overcome that. We could bring a raccoon in and they could do it for us. Okay. All right. I do have bananas. Does anyone want a banana? Bananas? I'm not going to throw, I feel bad about throwing a banana. I can throw a banana gently. There we go. No? Yeah, that's true. I was going to bring a knife in. Yes. There you go, banana. There you go. Okay. Just keep eating, essentially, for the next half an hour. We'll get through it. All right. So, things we can do. I don't know why they changed from those little twist ties, which were probably killing things. I don't know. Those little tapey things, they're not good. Okay, so we're going to, so here are all these things you could do. You could change the way edges are added. You can have probabilistic things. You will have a question about this. Of course, you have to maybe think about directed versus undirected. What's happening with that? Can you, as you move away from this particular mechanism, can you find other universality classes? Is it kind of stuck? And we know from Simon's model that there was a very tunable sort of story, right? That you could go, you just tune the innovation rate and you tune the exponent. It's really tied very strongly to it. That's not always true, right? At all of systems. Sometimes you have universality classes that are just really, there's nothing next to it. It's kind of like eigenvalues for matrices and so on. They're distinct worlds. Okay, of course this is what we're talking about. How do we, how does gamma get changed as we mess around with the model? Do you need preferential attachment? I mean, basically it's always there. All right, fine. So here's another mechanism here's a small variation of it that makes it plausible. And I think today will probably be enough for all of this, so we can probably start contagion on Thursday. So, all right, let me just give you a sense then of what else happens after this. So, one of the problems is that as you arrive, you have to have complete knowledge of the system, right? For you to choose which node to connect to, you need to know exactly all of the degrees. Then you have to sum them all up, and you have to randomly, and then you have to weight the chance of connecting to someone by the degrees. So that's hard, right? So it doesn't seem too bad because it feels like it is random, but it is hard. Okay, so you need the constant proportionality. So you need to know everyone's degree, and so then it's a big assumption. It's a big burden, a big cognitive kind of burden. So we can fix it up with a simple mechanism, and this is it. I know I'm flipping through this. So you allow nodes to attach randomly to start with, right? They just come in and it's like, I'm your friend. They're slippery, aren't they? Although usually, yeah, that would be a hard thing to explain in a hospital, that you slipped over while holding the banana. Okay, so let's see. So you're going to connect randomly to nodes. Just come in and say hi, which is obviously weird, but become friends with random people, and then you become friends with their friends. And that's where you get we'll see this more again with contagion. This is where you get your extra connection. So you also do this, you can also do that extra step at random. So you make random friends and then randomly connect with their friends. So that's pretty good. So we'll get this, I can talk about it a little bit now, but you get a different probability. I mentioned this at the start. So the probability that you connect to a node of degree k is now, when you're talking about the friends of friends, is now proportional to their degree, right? So this is so if you think about it like this, if you randomly jump on edges, this is going to be an important piece again later. So if you now, instead of selecting nodes, you randomly select an edge, do that, and then randomly go one way or the other, well, the chance of getting to a node of degree 5, there are 5 ways to get to that node, right? If it's got 100 friends, there are 100 roads to that node. So when you're selecting from edges, you have this improved chance, or this accentuated chance of getting to them. And what it means is QK, the probability that you get to a node if you've followed along an edge, a randomly chosen edge. So you jump on a random edge, take random choices to where to go, and then go to the end. The probability that node will have degree k is going to be proportional to k times the probability of getting a degree k node. So you have your probability of getting a degree k node, and then you have to multiply it by k, because there are k ways to get to it. So now you're choosing by its size, which is what we got for. So it's what we got for free when we chose cities by choosing the people who live inside them, by randomly choosing one person, and we got that, right? We got that increased chance of getting. City size comes straight into it. All right, so it's a rich gets richer scheme. And the thing is, now we have the k appears, right? So this specific choice of mechanism where you attach to a node proportional to its degree has this very natural way of coming about. I mean, we could say it's k to the 1.5, right? Or k, some power of k, or some sort of weird function of k. We could choose all sorts of things. But you can actually you can write this down and get a simple mechanism for why it could be linear. Right. Okay, so we'll see something later on, so that this QK, and which we'll get to and we'll drive properly, it means that your friends have more friends than you, which is very disappointing, on average. very disappointing. This is first noticed in, it's called the friend paradox, but paradox is probably not the right word. So, so someone else did this. It turns out that then you can think of attributes in general, and it depends on connectivity. So it's related to how many friends your friends have and so on. But if you have attributes such as wealth or, kind of anything, right? There's the paper that was done in particular was the number of citations people have on Google Scholar, right? So you have your co-authors, and then you have you have the number of citations you have, and then you have the number of their citations. So on average, an average person, their friends will have more citations than them. Obviously, there's someone at the top of the tree, and there are a number of people that look down on everyone else. But the way it's structured is that, and it's sort of a structural source of inequality, a particular kind of inequality too, which is that, the Joneses have more than you, right? So keeping up with the Joneses is kind of structurally built into networks and certain kinds of attributes. And first of all, it's that they have more friends than you, which is extraordinarily galling. And then on average, right, and then there are other properties. So this is weird, but it's to do with this piece here. Okay, robustness is a quick flip through this. This is I think it depends how you can change this work again in ways, and sort of maybe it's not so robust itself, but you can change in different ways, and things will may or may not hold. But this is a 2000 paper. It's Nature, so things were flying out at this point, right, taking off. So error and attack tolerance of complex networks, you can see, this just lights up all sorts. Everyone's worried about this or thinking about this. I know it is 2000, but there are great implications here for security and so on. Okay, so here's well, actually it's not a pure random network, I guess. It's an exponential, so they have exponentially distributed degrees, and here's a scale-free one. So again, you see that kind of the hubs are appearing. And the idea is, well, what happens if you start taking out nodes, right? And how well does this thing perform? So perform is an incredibly broad range of possibilities. There's structural integrity, there's a dynamics you can put a dynamic thing on top of it. How well does it hold up? You can think of all sorts of dynamics. Do they perform better or worse? And then what if you target them? So the kind of clear thing you might start to think about, well, if you target them and you take out the nodes that have the most friends, you're going to hurt this network more readily than you'll hurt this one. So random attacks, you're going to be getting a lot of these little characters in these nodes in these networks with hubs. It's going to be harder to get the hubs if you're just randomly attacking. So they're a little more robust under that kind of strategy. That's the story. But if it's targeted, then yeah. No? And let's see. So this is the story. So blue symbols are random removal, and this is complicated to look at. And red symbols are targeted first. So here are a couple of examples. This is some sampling of the internet at that time, and this is a World Wide Web. So let's see. So scale, this is hard to look at. This is the exponential graphs here, the triangle and the diamond. So under random failure but targeted attack, what are we measuring? This is the diameter of the network. This is the one time, so we talked about distances in networks. This is the diameter. So it's the longest, shortest path, which is a funny thing to say. It's the longest, shortest path in the network, which is a pretty fragile kind of thing, right? You are taking the maximum over many different paths, obviously, but it is a somewhat fragile beast. But it probably maximally sort of shows things changing, right? So it's well selected. Okay. Let's see. So triangles and diamonds. So either way, the exponential one doesn't really break, its diameter doesn't increase differently, right? So its diameter, its diameter is growing because you're taking out, you're potentially creating, right? You've got this blob and you're making it harder to get from one place to the other because you're removing. So you potentially, so it makes sense. You might increase the diameter. Eventually the diameter has to drop. if it starts to break apart, what do you do with diameter then? Okay, I don't think we got to that. This is a fraction of edges that have been taken out. This has to do something else eventually, not shown. But the scale-free one has very different behavior. So random attacks don't hurt it, really, because you're just sort of clipping off the edge, the characters that have one friend, typically. But targeted ones, really blow it apart. So it's kind of what you expect. And then this kind of characteristic is seen in a couple of real world ones, right? So, point is to say that these things are random failure. They're robust, but they're fragile to specific attacks, which is it's the robust yet fragile story, the whole hot model business. So it ties back into that. Yeah. So you have systems that, generally speaking, if you've characterized here's something where you want the way the environment acts on it to be random. That's fine. Now, okay, fragile to targeted ones. Hubs are a big deal, so it makes sense. Whether you should then go out and say, the world's going to collapse because anyone can do this, they just have to find the hubs. Well, that's hard, right? I mean, you can see them, but often they're hubs for, in their hubtasticness, they have become reinforced and strengthened and so on, right? So again, Google is this big distributed thing. We've had, and Amazon's the same. I mean, they're just incredibly, they've become very resilient because there have been attempts to knock them out, right? Just for fun. Like some kid in Slovakia runs a denial of service attack using zombie computers. Because, that's cool, right? So, or maybe for other reasons, I'm just speculating. Anyway, but that's happened over the time, right? That there have been denial of service attacks. I think it's less the case now that these things go down. Facebook probably goes down because of Facebook not being such a great bit of architecture. I don't know. Okay, so then those hubs aren't vulnerable is the point. Typically they aren't, or they get reinforced and strengthened and so on. And often they're not to be thought of as nodes, right? Google, it looks like a node to us, like Google, but it's a whole bunch of nodes masquerading as one. Okay, so most connected nodes are either physically larger ones or subnetworks of smaller, normal-sized ones. Okay, so you have to think about that. Okay, so I'm going to in the last 15 minutes, I want to entertain you with a different approach to this. That's really, really nicely done, and it's around the same time. It's 2001, so it's a couple of years after. And they expand the whole story. So now instead of, maybe I guess it's an AK sub I. So now we had probably of attaching to a node of degree I, so we make it A sub K. And they did more than this, but the sort of main thing they did was say, well, let's make it a power. And they start to explore what happens as you change the power and then indeed some other aspects of even linear, what we'll call linear kernels. So it's a linear kernel if it grows as K sub I somehow. Okay, so they looked at it, it's kind of odd what they were able to find. Okay, so we're going to use rate equations, and so it's so again this is the same as what we had for Simon's model. I'm just going to go through it. So the change in the number of nodes of degree K. So two things can happen. Nodes of degree K minus 1 get chosen. And this attachment kernel, this is the normalization factor, that's a probability that you choose them. The probability that you choose a node of degree K is here, this bit divided by A, and there you lose one, right? So you're losing one. It's moving out of that category. Plus, there's a 1 if you, there's a rate at which nodes are being added of degree, they're just K equals 1, right? So that's what they do. They're a very simple thing. Okay. So one node with one link is being added per unit time. That's this little guy, the Kronecker delta over here. So this is equal to 1 when K equals 1, equals 0 otherwise. So it's a nice way of putting all the equations together. And I've just explained these things, so this is what's going on. So A is the correct normalization. We'll have it on the next slide. And you can see it with some initial network and then let it go. Right, and A sub 0 is 0. There's no chance of being attached to if you have degree 0. Again, sadness. All right, so probably you get to a specific node, it's going to be its attachment kernel divided by the normalization factor, which is, I know, fun times. It's the sum of the attachment kernels for degree k nodes times the number of degree k nodes. Got to sum up over all those guys. And so for the Barabasi-Albert model, we had attachment kernel was just k, and the sum is quite simple, k and k. Yeah. We had this business before. We had 2mt. So this is the normalization factor. We had 2mt, but now we have m equals 1. So it does exactly what we did before. All right. Yep. Good. Okay. So now this is solvable. We had this, I'm going to scoot through this one. Now we did this kind of funny thing where we solved it on a per node basis before. Now we're going to solve it for categories of nodes, so nodes of degree k. So the number of nodes of degree k, we're going to figure that out. So this looks again like the Simon model in terms of how it's solved, although it will be rate equations. So it actually will be a differential equation story again. And then it's cleaned up. All right, fine. Okay, we look for a steady state. So we did this sort of sneakiness before, that the number of nodes of degree k will be some constant times t. It's just growing. And so we can replace the derivative. So it's really just d, this little constant dt is 1. So that just disappears. So it's a funny thing. We kind of popped out into differential equations, then we collapse back into a difference equation story. So it looks again like the Simon's model. So t, these guys all cancel once we put in replace these guys with little nkt. I know this is a lot. And we can rearrange things. There's a question, you can, maybe I'll delete that. You get the same result, okay? Fine. So it's a more general approach, and this k to the minus 3. So it's this very odd thing where it's just one value of gamma. So what happens if we mess around with this attachment kernel? Is this 3 universal within this kind of world? And we know things are going to probably change. So let's go to k to the new. And you have to do something clever here to deal with this. This is a bit harder. Yeah, this is a bit harder. And the reason is you don't know what the normalization factor isn't as easy. So the normalization factor before, we just had to know the number of edges that had been added, and then you have 2 times that number of edges, and that's the sum of the degree, right? So that's good. But how do you have the sum of the degree to the power of something that's not 1? That's why it's a problem. Okay. So there are 2 things we're going to do here. So yeah, we can relax the attachment kernel, so it looks like it's linear, but it's not quite, or it's got some messing around with it. Okay, so let's get these little pieces in. I know this is not fun, but I want to show you kind of the upshot of this. Okay, so we had 2t before. That's our normalization factor. Now we just know this. We have some horrible monster here. This could be k to the new. We're not really sure. What we do is we assume that it actually still grows as some multiple of t. Instead of 2t, it's some multiple of t. And then we have to check that that's okay later on. So we're going to make an assumption, solve everything, and then go back and see if it works. A little tough. So you can find mu later on. It's kind of spectacular. And we'll assume that we get to a steady state. Or it's growing linearly. All right. Okay. Yeah. Yep. So for k, we had k minus 1 and minus k. That was all good. But now we just have to put the attachment kernel in here. And instead of 1 over the attachment, the the sum of the attachment kernels, we have 1 over mu t. So that's going to clean up. So instead of 1 over 2t, it was 1 over mu t. So now we're assuming we can do this. And from that, you can actually rearrange it. You actually get, this is in principle solvable if you know what the details of these are, and this linear growth thing works. I know it's a lot. Okay. Right. There's a little offset here, but basically nk minus 1, nk, we've got these little guys here. So when k equals 1, solvable, we have a number of nodes of type 1, except for a function of t, a linear factor of t, growing as mu over mu plus a1. You can just solve this guy here. And k greater than 1, we just have nk is some factor times nk minus 1. So we need to know the details of this. Okay, it's a lot. I'm not going to give you these questions. Yeah, I won't do that. You get this result, and this is kind of pretty spectacular, but you get nk, it's growing in this way, and you can show that it's k to the minus mu minus 1. So when mu is 2, we have the linear attachment thing. Mu is 2, and we have a linear attachment 1. We get k minus 3. So that's good. It collapses back to that. But now we're seeing that this mu is going to dial away from 2. So the details are going to matter, right? So that's sort of the upshot of this. The details will matter, and we can kind of get everything. We'll show you these things. We've assumed this, that the sum at any point in time is growing like mu t. We can put in our linear growth for the number of nodes of degree k. Yep. And we can get this closed form expression for mu, which is pretty bananas, but it's this. Yeah. Mu looks wrong, doesn't it? No, it's okay, I guess. All right. So there's a mu sitting in here. So this horrible thing, in principle, can be undone. It's closed form. You can play around with a little bit, but it's kind of this bananas thing. So 1 equals this horrible thing here. You have to find the right mu to make this 1. So they really turned it up. That's basically what happened, right? So we can solve for mu in some cases. It doesn't seem to be too horrible, but it's definitely somewhat horrible. Okay, so this is a strange business. So let's try this attachment kernel. A1 is alpha, and this is a dialable parameter, and then AK is k for k greater than or equal to 2. So if we replaced alpha with 1, we'd be exactly back at the Barabasi-Albert model, right? Everything would collapse back. But now we're going to just dial up the importance of attaching to the desire to attach to nodes of degree 1. So we could make it 0, so they're never really found, right? Or we can make this alpha infinity. This is not right. This isn't a probability. It's a weight. We can dial this weight up as much as we want to, sort of force the new nodes that are coming in to attach to degree 1 nodes. And so you can imagine what's going to happen. So if alpha goes towards 0, then the little guys are not getting new friends, and so it should be more and more skewed. Right? There'll be more of a rich gets richer. As alpha goes to infinity, you're really forcing the new nodes that come in to attach to nodes that have 1 friend. So you're going to keep it pretty, so this is sort of alpha equals infinity is more of the socialist one, and alpha equals 0 is the capitalist or the monopoly kind of one. Okay. Crazy things. You can find out that gamma is mu plus 1 from this, right? Simon 8 sounds terrible, doesn't it? And that you get this ridiculous closed form expression, actually. So mu over alpha, this is an important result, but mu over, so depending on alpha, you have this closed form expression for mu, gamma functions, right? And this is solvable, and you end up with this bananas thing, that mu times mu minus 1 is 2 alpha. And so this is a quadratic in mu. You can solve that. So mu is 1 plus 1 over this square root up here divided by 2. So this is one bananas example that you can follow through. and sort it out. Let's see, so when alpha equals 1, then we're back at the Barabasian model. So that's 1 plus 8, square root of that is, so square root of 9 is 3, so 1 plus 3 divided by 2. So it's 4 divided by 2 is 2. So that's good because we're back at mu equals 2. 2 plus 1, gamma equals 3. We're back at that silliness. All right. Okay. And so since mu is between, since gamma is between gamma is mu plus 1, and you can see from here as you go from 0 to infinity, you go from 1 to infinity. So, did I say that right? Yeah, alpha is between 0 and infinity. Gamma is between 2 and infinity. So so this is kind of surprising, right? So we have a linear attachment thing, but we can really tune it all over the place. We can get all these different universality classes. So the details really matter in how these networks are being built. All right, I have just a couple more pieces to add to this. Again, we're not going to do any derivations because it's horrible. So sort of beyond what we're doing here. So if we get somewhat richer, we'll dial nu down below 1, right? Nu is less than 1. So let's say it's to the power of a half, right? So you're attaching to people who are wealthier or have more friends. In this case, that's what it is. But the bias isn't as strong. Then you end up with, again, a power law, but it has this exponential attached to it, which truncates it. So it's a power law, and then it gets crushed. And these are stretched exponentials, lots of... actually, funny thing is, now you get universality. Now the details of the distributions don't matter. It really locks into this behavior. So that's good. So there's a universality providing nu is less than 1. So on the other hand, I'm not going to show this, don't worry about that. The rich get much richer. So, right, so we're going to say, yeah, and we'll allow nu to go above 1. I mean, if it's squared, cubed, right? So you're wanting to attach more and more preferentially to the richer ones. So now you get to winner take all. Suddenly you get to winner take all, actually. So if you dial mu just a little bit above 1, suddenly it's winner take all. So there's going to be one node that's going to dominate everyone else. They call it a gelation phase. So this is a really important thing to understand, right? So that, yeah, you get all the power law things for nu equals 1, and you can get all sorts of things if you change the attachment structure. But as soon as you make it attach a little superlinearly, the thing just goes berserk. There's a winner that just crushes everyone else. And for nu greater than 2, everyone essentially attaches to this one winning node. It's just a finite couple, like 3 or 4 that don't get attached. It's a finite number. So it's complete domination at this point. All right. Okay, so that's good. And so let's have a nutshell. I'm sorry, I know there's a lot of math involved with that, but I think these last points are really, there's some pain to get there, but these are things to really take home. Okay, so this is for models of networks, and we're going to move on to contagion. So obviously we have graph theory. We're talking about how things grow, so it's more of a physics, stat mech kind of flavor, computer science as well. You want to describe how these things work, we want to explain, and that's a good example of where we were just then. There's sort of this smorgasbord of things that seem to be important. Degree distribution is the big deal, but other pieces, clustering, associativity, obviously the overall structure, modularity is a huge thing. There's a lot to be done. There's still an enormous amount to be done. So temporal networks that are unfolding now, right? I mean, obviously we've talked about temporal networks there, but ones that are kind of edges are going in and out and all sorts of things. That's only just sort of a couple of years now that people have really gotten into that. Okay, so I think it's time to go. I can show that slide next time, or as you leave. But so good. Thank you for bearing with that one. Contagion is next. We'll talk about contagion. Come on, show me the thing. All right, people. Spreading of diseases. Topical.